which is commonly known as IIO, in the Linux kernel. Uh, and we'll be seeing the how IO fits inside the Linux kernel architecture, uh, how basically it's managing its component and how it's getting connected with multiple sensors or the data converters, and what are the different use cases and its architecture. So let's start. What? Let's see our agenda first. So first, we'll be understanding that what's Linux. So many people are confused that what's a Ubuntu, what's a Linux kernel, what's a Fedora. So we'll be understanding the Linux versus the distribution, and then we'll be seeing the Linux subsystem, and then we'll be seeing the uh, IIO, which is one of the subsystem inside the Linux. Then we'll be seeing the architecture and the core concepts of the IIO drivers. And then we will be seeing how basically we can write a basic IIO driver, then its advanced features and the real-time application. So let's understand Linux. So basically, Linux is consist of kernel and uh, shell. So uh, basically, different companies or which are known as distribution itself, they came and they modified the they have taken the core Linux kernel and they have modified the shell as per their need or based on their requirements or based on the customer's requirement, and they distributed those to the users. So let's first understand what is Linux kernel. So this is basically an open source. First, it was launched in the year 1991 by Linus Torvald, uh, and he was basically motivated with the Unix core. So Unix is basically something which is very much similar like Linux, and that was developed before Linux. Uh, but that works on a monolithic kernel, whereas Linux works on a hybrid kernel. And that was the main reason Linus Torvald developed Linux. So the kernel is basically the core of any operating system. So if we say Windows, so Windows is also having its own kernel. If we say Mac, so Mac also is having its own kernel. So basically that's a core part of the operating system, which is consist of the middleware and the driver. So it don't give you any graphical user interfaces, but yes, if you need any graphical user interface or any network management, so everything is basically getting managed by the Linux kernel. So uh, it basically manages the hardware resources. For example, your USB pen drives, your USB keyboards, your Bluetooth keyboard, your mouse, your display, your uh, any HIDs or any add-on hardwares. So almost, any hardware of the system is managed by the Linux kernel. Then software processes and memory. So when you're seeing, I'm displaying something here. So basically, I'm running a PowerPoint now. So that's basically a process. So this process is also managed by, because in the background, a lot of things are running in the system. Because I'm speaking now and my voice is getting captured by microphone and it is getting transmitted over the air and received by the Bluetooth transceiver in the system, and that then it's getting converted into the data stream, which is getting pumped over the Ethernet, and it's getting pumped out of the system. So, in the background, a lot of things are going on. Plus, it's displaying. I'm able to see my slide. So it's not just my voice. The data which I'm displaying over here is also getting pumped out through the Ethernet. So there are a number of processes running in the background and in the foreground. So everything is managed by the Linux kernel. Apart from this, it's managing the middleware as well. A middleware consists of file system. So especially for Linux, it supports so many different type of file system, more than Windows, because it's having its own file system. Plus, it supports Windows file system as well, like FAT32, FAT16, and TFS, and Linux file systems like ext4, ext3, as well as it supports the security features as well, like cryptography using OpenSSL, WolfSSL. Next, let's understand about the distribution. So, as we spoke earlier, so there are different distributions available, like Ubuntu, Debian, Fedora. So they basically developed a complete system around the Linux kernel, and they have customized as per um, the user's requirement. So at that particular time, they might have gathered the information from the users that what they want, which kind of um, environment they want, which kind of user interaction they want, which kind of software installation tool they want. Based on that, they have uh, designed their shell. That is basically called as shell, which we're talking about, the distribution. And the Linux kernel remains same. So the basic core feature of the OS remains same, but the user experience varies based on distribution to distribution. Okay, so what distribution includes? It includes the graphical user interface that may be like K desktops, genomes, or there are something called Qt-based desktops as well. Today in embedded systems we are seeing. So um, actually, the main reason of the popularity of Linux is because of it's open source and highly customizable. And a particular community, basically they are called as the Open Embedded World. They have taken this kernel source and they have customized this for the embedded system, and they provided a tool called Yocto. So Yocto is a tool basically which is not a distribution, but it helps you to create your own flavor of Linux. So apart from Ubuntu, Debian, Fedora, I can say Red Hat. Apart from all this, you can create your own version of distribution. So today, many companies are doing that. Those who develop the embedded systems, so they take the um, they take the Linux kernel, they develop a distribution around this kernel, and they distribute it as per their requirements. And they do it for a very much customized hardware. So, I mean, they can customize Linux kernel as well, not just on the only the shell. So, for example, there is an embedded system, and in that, if you don't need the USB 2, or if you don't need Bluetooth, or you don't need the Wi-Fi, so you can disable all these features there from the Linux kernel itself. That will helps to make the system very much lightweight. So you are basically removing all the unnecessary uh, core functionalities from the kernel. Uh, if required, suppose if you are having your own customized hardware, then you can add those in the Linux kernel in the form of device driver. So when we set a Linux device driver, so those device drivers are residing along with the Linux kernel. So if you see on the right side, this is basically a architecture of Linux. It's basically the expanded form of the Linux architecture, because Linux architecture basically divides into two layers. The upper one is called the user space. So if you see the top two layers here, the distribution layer and the software and desktop layer. So these two are basically the part of Linux user space. And if you see the bottom two layers, the Linux kernel and the basically the hardware. So These two basically are the part of Linux kernel actually. So here there's something I missed. Basically, these are the hardware drivers, and below definitely this there will be the hardware. So this hardware layer is basically sitting on the, or I can say this has a hardware abstraction layer. So here the there is a specific, a very much specified layer of the Linux kernel which is abstracting the hardware. For example, when you are using your web browser, so irrespective of Wi-Fi or cellular or Ethernet, it is basically streaming your data. So this hardware abstraction layer provides you those features. So basically, the application don't care about the hardware. It basically interacts directly with the hardware abstraction layer. And hardware abstraction layer basically routing your data to the available port. So if you're connected to Wi-Fi, then it will stream your data through Wi-Fi. If you're connected through the Ethernet, so it will stream your data over the Ethernet. So that management is done by the hardware abstraction layer. Now, next coming to the yes, so excuse me. So let's talk more about the hardware abstraction layer. So basically, it's again having two layers. So the first layer basically gets the data and routes based on the available resources. So on the bottom part, it's also having the extremely low level drivers, which is basically managing the specific hardware, like Wi-Fi drivers for managing the Wi-Fi hardwares, the Ethernet drivers for managing the Ethernet. And if you are connected to a mobile phone, so you'll be having a cellular driver, which is basically interacting with your 4G or 5G network. So that's having a different hardware altogether. So these are all three different hardware through which basically data is getting, I mean, your device is getting connected with the internet. Now coming back to the Linux kernel alone. So this is the upper part, which basically manages the middleware. So I mean here the like all the file system. So basically when you suppose you connected a pen drive to a system, and you have a hard disk as well, and you have suppose um, a memory card. So mostly if you are in a Windows system, so you'll be having an anti-FS file system in your local disk, but mostly pen drives uses the file systems. So when the user is trying to save some file, so it is using the file explorer. That is also a that is also an application, and application don't care that how basically you are going to save my data. It just gives the instruction. So for application, it is having the same command. Either you are going to save the file in your local drive, or you're trying to save the file in a pen drive. So the application basically the when application sends the command, it goes to the Linux kernel, and there it decides that what file system you are going to use, because based on the hardware. So it see that you are going to save in your D drive, which is a USB pen drive, and it's having a FAT32 file system. So then it uh, selects the file system as FAT32 file systems, and then it passes to the hardware abstraction layer. That's the green block. So the hardware abstraction layer takes care of basically saving the data, because kernel won't take care of how the data is getting managed into the different sectors of the hardware. Because if you see any physical devices, it's also divided into the raw sectors, which is 512 byte each. So these are basically the flow. So I will just pause here and uh, just want to ask if anyone is having any question from this topic. Any question so far?
I just have a simple question, like
Sure, sure.
how far it has come, because we know on the applications which are visible, like Windows 10, 11, and all,
Mm.
iOS versions keep on increasing, right?
Yeah,
But
yeah.
because since it is behind the screens, we don't know much about the kernel. Is it been that improved a lot? How far it has come?
Uh, I didn't get your question. Can you, elaborate your question, please?
Yeah, so to add to that, like for example, say for Windows 98, we
Hmm.
could add a kernel which is of that time made, right?
Okay, okay.
So
Got
with
it.
every version of the
Hmm.
operating system, do you come up with a kernel, or do you have the kernel journey taken all together separately?
Okay, okay. Got your point. So I'll just say one thing. So these are basically very loosely coupled architecture. So in a loosely coupled architecture, what happens? The two software components are, mm, I mean, very loosely connected with each other, so that you can replace them very easily. Okay, and those are, though it sounds loosely coupled, but these are known as very good architecture for for any kind of software development. So the Linux follows the same. So today, what happens? The Linux kernel, if you see, every 3 months they keep on releasing the new versions of the Linux kernel. So the latest one is 6.17, and it has been improved a lot in 1 decade. So a decade back, if you go, it was like 2.6 version. So, and 1 decade back, if you go, so 2 decade back, so it was 2.4. So 2.4 to 2.6 took 1 decade, and 2.6 to 6.17 took another 1 decade. And the architecture wise, it has changed a lot. They introduced a lot of uh, I mean, uh, we say the system calls, lot of system calls which was there in Linux kernel has been moved to the user space. A lot of new drivers has been added, and uh, one very important point. So if you look into the cryptography, so a lot of old cryptographic libraries or tools has been obsoleted. So those has not been actually removed from the Linux kernel because they support everything. So they have those features, plus they added the new features as well. For example, the support of SHA-256 as a SHA-512 checksum. So these are supports has been added. Plus, it is still supporting MD5 checksum. So those are, there are different ways to remove those old cryptographic libraries for security reasons. So, yes, they keep on adding a lot of security patches as well. And since every day you will be seeing new hardwares are coming into the market. So the Linux, the Linux distribution team, they are working along with those companies, and they keep on adding those features in their Linux kernel support. So in the new version of the Linux kernel, you will be finding those new features. I'll be giving an example. There is a company named Pure Li-Fi. Okay, so they developed a new technology called Li-Fi, which is basically an alternate of Wi-Fi. So Linux kernel used to support Wi-Fi because Wi-Fi is an old technology. So when this Li-Fi has come, so the Li-Fi team also started working with the Linux kernel team, and they launched their own Linux drivers. So now, from Linux kernel 6.12 onwards, it supports Li-Fi as well. So very soon you'll be seeing in the new mobile phones Li-Fi is there. So if you will be having, because Android phones are also having running Linux kernel inside. So the by default, the Android will be using those Li-Fi drivers. So if someone is having an older Android version and they want to upgrade, so they have to install the drivers. That used to happen in your Windows machine. So if you suppose nowadays, even if you see in the Windows machine, they keep on giving you the updates because they started following the same concept of what Linux is following. So if suppose new hardware is there in the market, they will develop those drivers and they will pump you through the software updates, and your system will get updated with those drivers. Earlier, you might have remembered, earlier we used to, whenever we used to buy add-on hardware, so those used to come along with some CDs, and we have to install those drivers along with those drivers in the Windows to basically make use of those hardwares. So did I answer your question?
Yeah, pretty much. Thanks a lot, Zafar. That was so insightful.
Sure. So I'll just go to the next slide. So let's understand about the Linux subsystem. So basically, the Linux subsystem is it's a specialized component of Linux kernel that manages very much specific aspect on operating system. For example, like memory management. So these are something very much uh, inside the Linux kernel. So when we talk about the user space application, so we talk about the applications there. So like a web browser. So we have a Mozilla, we have Google Chrome, or we have the Internet Explorer. So these are something which are basically the different web browsers. So we talk, these are the different applications in the user space. But when we are talking about the Linux kernel, so we will be talking in terms of the subsystems, like the memory management, like the scheduler, like the HIDs, like the networking stacks, uh, process management, and IIO. So IIO is also one subsystem there. So when we talk about, so I'll give you some examples that will be helpful to understand what is ANSYS subsystem. So when we talk about the network stack, so there are different networking subsystems in the Linux. Uh, it's there in other embedded system as well, but they don't use the same which Linux is using. So Linux might be using the Apache's TCP/IP stack, or uh, some version of the Linux is using uh, a very much. It's called LWIP. That's basically used in the microcontroller Linux. So the LWIP, the lightweight internet protocol, the LWIP stands for lightweight internet protocol. That's used by the RTOS. So RTOS are basically meant for real-time operating system. The expansion of RTOS is real-time operating system, and those are basically meant for small footprint embedded systems like microcontrollers. So there are certain variants of Linux which runs on the microcontroller. So those are all called as MUSI Linux, microcontroller Linux. So they use the LWIP stack, and that so there basically we are removing the actual component of networking stack, and we are bringing the customized version of networking stack. Similarly, we have the memory management. So memory management is something like when you are running Linux, we can't develop, we can't uh, basically port every component for n number of targets. There are n number of targets for which the Linux is running. So memory management is a subsystem which takes care of your available memory, and it makes the Linux to run on it. It basically helps the uh, Linux to adapt based on the mm, RAM or the memory available. For example, when you see, you can run the same version of Linux on a 16-bit 16 GB RAM or 8 GB RAM or a 32 GB RAM or a 64 GB RAM. So the same installer is getting used. You don't need basically a different installer for these different type of hardwares. I mean, in different type of hardware where your hardware configuration is getting changed. So these are taken care by your memory management based on your available memory, because every time at the boot it see that how much memory you have. Based on that, it is basically loading the different subsystems and keeping others on the swap location. So there is a swap location which is basically based on a virtual memory and paging concepts. So uh, if anyone is getting any doubt based on this paging or virtual memory concept, you can interrupt and ask me about those. So let's understand about the IO subsystem, because our main core topic for today is the IO subsystem. So we'll be understanding this now. So the overview. The industrial IO is a Linux kernel subsystem and a framework that unifies the communication with the sensors and the data converters. So basically, the reason for choosing the IO subsystem is it is basically a proven subsystem and framework. So that makes the life easier for basically a developer to to integrate any sensor or any data converters. Data converters I means like analog to digital converters or digital to analog converters. So using these two, using this particular framework and the subsystem, it takes very less time for the user to, uh, I mean, j- uh, develop a driver for the Linux, because Linux device driver takes it's basically a very lengthy task. It takes a lot of time to develop because there are a lot of aspects which a user has to take care. For example, suppose you are developing a Linux driver, and I speak about a traditional Linux driver. So in that, what happens? You have to basically take care of, uh, I mean, memory management, then interrupt management, then synchronizations, data handling. If data is coming very much fast, you have to maintain those data in a buffer. So the IO subsystems provides you all these features. So you have to just configure and hook up your core driver with them. Unless if you are developing I will if just give a small example. Like if you are developing a for a particular sensor X, you are developing a core, the traditional character driver, and if you're developing a IO driver. So the difference between these two will be like almost 50% in terms of time. So if it takes 6 months to develop a Linux character driver, it will take only 3 months for you to develop a IO driver. The reason is the already available framework, which I already told you, like buffer management, interrupt management, data handling, uh, yeah, all this. So this basically divides into two part. If we talk about the IO model, so this is basically dividing the driver or the architecture into two core parts. One is called as device, another one is called as channel. So we'll be seeing this in our uh, maybe in our demo and in upcoming slides. So I'll just give a small differences between them. So the device is basically the top level entity. So whenever the user see anything, any IO device, so it will basically the first thing which will appear is like IO device. So IO device basically so IO and colon device 0. So these names are basically choosing by the Linux kernel. So we don't have any control on giving this name. And this is one of the cons of the IO driver. Whenever you are developing a character driver, So you basically you can choose the name, whatever the name you want to give to a character driver, but that option is not there with the IO driver. So whenever we have to probe, or whenever we have to hook up our uh, any of our application with the IO driver, so we have to first ask, and first we have to read the name of the driver. So there is a way we can find, we can read the name of this driver, and then we can connect our application to that driver. So each driver basically can have it can or it may or may not have different channels based on the hardware. So for example, if you take any ADC, and ADCs comes with different channels. These are all physical channels. So during using these channels, you can measure the different voltage levels, current levels, or any physical quantities using the ADCs. So suppose you are taking, I'm just taking an example of ADS 1115. This is one of the most uh, commonly used 16-bit ADC. So it's having 4 channels, and each channel you can connect to different uh, sensors or actuators or anything which you want to measure. So in that case, you can map those channels as the software channel here. So if we talk about our time of flight sensor, VL53L1. So this is having a single channel, a single physical channel through which we basically measure the distance. So basically uh, that particular device can have only one channel. We cannot create multiple channels for that particular device because physically it contains one channel. So the same channel we map to our software, and which is basically getting exposed to the user space, and user space application via this path, they can read the distance. So it is having only distance 0, no distance 1 here. So common sensor and the data acquisition use case. So in the industrial automations, basically because I is having uh, a very well proven framework and subsystem, so it can be quickly be used for developing the drivers. So mostly in the industrial automation, in environmental monitoring and medical instrument, uh, people are using this framework for developing their devices. And the another reason for making use of this is they are having 2 different ways of interaction. One is via sysbus, another one is like character drivers. So the character drivers used to have one more advantage earlier, like for any high-speed data streaming, the application used to use the character drivers. But the for on IO devices were used only for low streaming data or low speed data, and only for configurations. But this used to happen earlier before kernel version 6. So in kernel version 6, the uh, I mean the feature of IO has been enhanced, and now the IO driver is supporting character drivers as well. So it's having both the features, and it is giving the user of flexibility to interact both the ways via sysbus or via character drivers. So it's today the IO drivers and IO supported devices are used for both in both the use cases, like high speed and low speed. So here I'm just going to show you again the different subsystems of Linux. So here the user application, which is basically the shell, the command line, the graphical user interface, the other entities like networking configuration tools and all. Uh, and in between, you have the system. call interface, the sys calls like open, close, IOCTLs, read, write. So those are all like call as system calls. So unlike other or plain embedded system, user space code, which can be a C code as well. So that cannot interact with any of the kernel subsystem, which is again a C code. So if any user application code has to interact or has to drive the kernel space code, then they have to go via system call. There are no other ways. So in Linux subsystems, we have discussed about the IO subsystems, the inter-process communication, which basically helps two different processes to communicate with each other, and then network stack, the virtual file system, the device drivers, the memory management, and the process management. So, okay, I'll just pause here once again and will ask if someone is having any question. No? Okay, I'll proceed then. So now we'll be discussing about the architecture and the core concept of the IO drivers. So the key components of the IOs. So as we discussed in the previous slide, the device, which basically represents the physical sensor hardware that captures the environmental data for processing. So basically, uh, like as we saw that any IO supported devices appears to the user as a device. So from the top level, we see the device. And when we have to interact with the device, we have to go further down to the device. So if you see this, so if you see, I mean, these two lines, which is in blue color, so you'll be seeing up to some extent the path is same. So the first one appears shows the device, the top one, and the another one shows the further attributes of that devices. So one of the attributes you are seeing here is the distance, which here in this case is the channel. So it can be anything else. It can be like uh, it can be your name as well. It can be some more attributes using which set the different um, we can set the different uh, parameters inside device parameters, I can say. So the next is the channel, which is actually one of the attribute of the device. There are two more things which we have been discussed so far. That is the trigger for the data capture. So uh, these are all software component, whatever we are talking about, because we are talking about IO subsystem, which is one of the Linux kernel subsystem. And Linux kernel subsystem is basically a embedded software, or I can say it's a software. So the different aspects here is like the device, the channels, and the triggers. So this trigger can be so basically this triggers can be any interrupt or hardware. It can be hardware interrupt or it can be software interrupt. So these are certain features within the subsystems, which basically is designed to capture the hardware triggered interrupt or software triggered interrupts. So in case of a uh, like a traditional Linux driver, we have to write all this trigger handling with our own. But the IO subsystems provide the complete um, framework where basically you have to just specify the name of your uh, data, I mean the trigger handler. I mean, if the particular trigger happens, then what need to be done? So you have to specify a particular function. So the function can be getting called whenever the trigger comes, or you can basically there are certain standard functions as well, which you can hook up directly with the with those triggers, so that they will do the job on the behalf of you. So you have to just configure it. Next is the buffer. So the buffer management is well taken care by the IO subsystem. So for example, if you are receiving the data from a very fast, from a sensor which is pumping the data very fast. So at a time, if you are going to write your own, data handler, there is a chance that you can miss the data. But in the IO, they have a ring buffer. So we'll be seeing in the next slide. It basically handles the data in a circular buffer. So it keeps on filling the data into the circular. So if one buffer is filled, it will just pass to the another one, and it keeps on filling. And suppose the user is not reading, in even in that case, what will happen? If the circular buffer is filled, it will keep on overriding the previous data. But in general, if the user application is keep on reading, so it will keep on. So as soon as the user application is reading the data from the data buffer, it will clearing the data from the data buffer. So one side, the trigger is keep on um, getting the data from the sensor, and this buffer management basically will keep on filling the circular buffer, and on the other side, user application keeps on reading the data from the circular buffer. So if the user application is on, so there are very less chance that you will be missing out the data, because these circular buffers are configurable as well as they are large in size. I mean, it's I mean, so basically, if you know that you are missing the data, you can even reconfigure to increase the size of the circular buffer. Okay, so this is basically the typical architecture of the Linux IO subsystems. Here, the other components are not shown, only the IO components are shown. So if you see the application, it interacts with the system call, and then system call interacts with the kernel framework. So the kernel framework basically consists of the virtual file systems, the character drivers, and the sysfs. So the character driver and the sysfs here basically uh, representing IO only, because IO allows you to interact both the ways. So basically, if you have to interact with the character driver of the IO, so you have to go to /dev/IO and device X. It can be 0 or 1, anything. We'll be seeing that while we'll be having our demo. Next is the device driver, which is again residing on the kernel space. So this is basically here in the IO subsystem is consist of three part. So the ring one is basically the buffer manager, which I just know spoken about. So ring, the name is basically saying the ring means it's a circular buffer. It's in the form of a ring. So which is again very much configurable. So when your sensor is pumping data very fast, then you can uh, keep on the buffer management manager will keep on logging the data into this ring buffer. And this IO trigger. So I'll be talking about the core letter. So the trigger is basically depends on how your sensor is sending the data. So whenever your sensor is sending the data, which is based on an interrupt. So first, as soon as your sensor is sending the data and it's issuing an interrupt that my data is available. So IO subsystem is having a mechanism. It's a framework internally supports the mechanism of handling the interrupt. So user has to do nothing. It will just configure the trigger. So as soon as the interrupt arrives, it will make the data to get filled automatically into the ring buffer. So we will not be writing a code for this. All the code is already written for this one. So ring and the trigger, this both works in together. But it doesn't mean that a ring always need the trigger. Your system can be based on poll, not on the trigger. So that time also, your ring will be working based on the poll. So if it keeps on polling and feeding the data into the ring. Next is the IO core. So IO core is basically the device registration. So whenever you are writing your drivers, so you have to basically you need some start point, that from where your driver starts and with what it is working. So one very important point need to understand for the IO drivers. These are definitely called as drivers, but they have to do nothing with the low level side. Yes, they provide you all the features which a hardware can have, like a trigger, like a I mean the channels. Okay, so it is a very well defined framework which can be getting fitted very easily with your hardware. But it has to do nothing with the hardware. They don't directly never uh, interacts with the hardware. So they give you a feel that you are directly interacting with a hardware, because it gives you channels through which you are controlling a device. I'm sorry. So next is the IO device driver. So IO device driver is the again a middleware, is the portion of the code which interacts with the bus driver. And your bus driver can be I2C, I3C, SPI, or it can be anything. It can be USB as well, or it can be SD protocol as well. It can be anything. So here you can see this is completely a middleware, even the IO driver. So IO driver will interacts with the bus driver, and the bus driver is the low-level driver which actually speaks with your hardware. Okay. So I mean, so far, any question? Something, anything from IO framework, or anything from what is bus driver, what is IO driver, anything?
So one question here.
Mhm.
So character driver is also provided by the framework, or you have to write and plug in separately?
Yeah, no, it's provided by IO driver in this case. But if you want to write a generic, very much generic character driver, so you can develop your own. But that takes plenty of time. You have to basically go through a lot of documentation. But in the IO, there is a minimal function, just a few APIs you need to call, and it will enable the character driver for you.
Okay. So, but
Yeah.
that would be very much device dependent, right? Based on which device you are.
It's not device dependent. These are basically something which is very much middleware thing. So the thing is, like, it is you who will be writing this part, the interaction between this bus driver and the IO driver. And apart from this, here on the top, the IO core basically will also be done by you, but it will be very much as per the hardware. Yes, this will be very much as per the hardware, but you can even fake also. You can make them full, and you can create multiple channels. Okay, but because user will be seeing the device through the IO. So you can say that your device is having four channels, but physically there won't be four channels existing. There is only one channel existing. So yeah, I mean, it is completely user programmable. Okay. So when you are writing a code for IO core, so you'll be writing some minimal code where you will be basically creating the different channels. And once this driver is ready, those channels will be appearing to the user space. Okay. And suppose you are creating some dummy IO driver. So in that case, you can show that you are having four channels, and it will be four channels will be appearing on the user space. Okay. So, but what happens in actual, everything is like all the command which is coming to the from the user space to the IO core via the system calls will be there within your code only. So you can do whatever you want with that with those codes. So in the real time, when you have a specific hardware and suppose it's having four channels, so you will be exposing those four channels. So first you will be writing, you will be hooking up your code here between this green and the red line, the pink line, pink block. So here basically based on the device, I mean, but okay, here you're not defining that how many channels are there. You're just defining the bus. Okay,
Mhm.
and here in the IO core, you are registering four channels. So user, whenever they will be so basically you are opening a path to the user, for the user to interact with this hardware via this all calls. If you want, you can even um, remove those channels as well. Suppose the hardware is having 4 channels and you just expose 2 channels only. So the other 2 channels won't be used. You'll not be able to see those other 2 channels, and user will not be able to see that at all.
Okay, okay. And so this character driver also like might ultimately interact with I2C and all, right?
Yes,
That is not
right.
shown here because it's all embedded inside.
It's all embedded inside. Correct. Correct. So we'll be seeing that quickly in our code. So, okay, as we discussed earlier, so basically it's having 2 ways of interaction. The very safe way is to go via sysfs, but it's not just limited with the sysfs as well. You can go via the character driver as well. So when we let's see that how we can develop a very much basic IO device driver. So basically, you need to set up a Linux kernel environment. Suppose the easiest way I'll be suggesting you, suppose you want to learn the Linux device driver. So you can basically get a Raspberry Pi, maybe the latest version, which is the 5, and you can install the Bookworm OS. And you can, in your development system, you can install the latest version of the kernel. And you can uh, build your driver against that kernel, and you have to transfer that kernel to the target. So, uh, I mean, I think this may confuse you, so I'll just go and show you in the real time. So before I show you my code, I will just talk about a little bit about the development environment. So until last year, I used to use the VMware for developing all the Linux related applications. And from this year onwards, I moved to the advanced development system, which is within your Windows machine. So all the new version of the Windows are supporting this Linux subsystem that is called as WSL, Windows Subsystem for Linux. So if you install it, it will appear in your system like this. So this is basically this is one of the very good move from the Microsoft. Instead, installing a heavyweight VMware or VirtualBox software in your system, you can enable, because you have to install nothing. You have to just enable this feature in your Windows. So you can enable Windows subsystem for Linux, and it is basically, it will be acting as an application, and it can take the advantage of your complete, uh, complete Windows resources. So if you open, it will just open in a terminal. But suppose if you want to make use of this graphically, you can just type the keyword Explorer and dot. Then it will open the Windows GUI here, and you can access all the folders. But this folder, this folder Explorer, which opened for me now, is within the Linux. So here, all the Linux command will be running. So this is full-fledged Linux within the Windows subsystem without any graphical user interface. But there is a way you can install the graphical user interface as well. But that's not needed because we have VS Code, and if required, we can just open by using the Explorer. So I'll go to my Raspberry Pi, and here, first I will take you to the kernel part. Okay. So if you install the bookworm directly over your Pi, so you can pull this kernel from the Py's repository, and this is the latest version of the kernel. So once you build it, so it will create the Arch. It's ARM64. So this image, this is basically the kernel, finally compiled kernel. So you have to transfer this to your running system. Uh, and then whenever you are building a Linux driver, so you have to build against it, because uh, what happens in a hybrid architecture? So this is not a monolithic kernel. This is the hybrid architecture. So in hybrid architecture, you can attach your uh, kernel code with the running kernel. It's not like in a monolithic kernel like Unix, you have to compile everything up front and you have to transfer that fully compiled single binary into the target. But here in this case, you can have a different other binaries which you can attach during the runtime. It's not necessary that you have to build everything upfront while in one shot and then you have to flash everything on the target. So this is the main kernel, and the other drivers will be getting attached during the runtime. So this is the complete source of the code which you can pull from the Git. Then I go to the view of the drivers. So here you see, just I will take you to the normal traditional GPIO driver. It's better I will go through the VS Code. It will be easy for me to show. So this is a character driver, and as I told you, here you can choose the name whatever you want. This is fully based on us. Like you can give a string name. So whenever I'll be using this driver, so I will be compiling it, and once I attach this with the running kernel, so under the /dev, this name will be appearing, and this is a kernel character driver. So this is a very minimal kernel driver, but if you see all the code you have to write with your own everything. For example, like is registration. So registration will start with init. This is the constructor. So the concept of constructor was initially bought by Linux using the C code alone. No C++ code is involved here. So then you have to write your own interrupt. You have to write your own read IOCTL. I'm not making use of any read, but I'm making use of IOCTLs. So IOCTL is basically a small read-write performance. It is a small read and write of the data from the kernel and user space. So this is just driving a simple GPIO port. So this is a destructor. So you need to provide some small informations. So when the user application has to call this, so they will be calling the system call. That's name is IOCTL, and that will call on return this call device IOCTL, and then here what happens, whatever the argument you have passed. So if you want to turn on off the GPIOs, you can basically send the command. So the command is the number here. This is the command. I mean, what you're going to do and what you want to do. So here is like the command, which is basically the the GPIO test, or it can be, these are all just enums. So it can be anything. It's fully user programmable. So here, basically, I'm just passing one command. That means testing the GPIO 7. It can be anything. I can enhance this in the future for other GPIOs. I can send another command. The value of this GPIO, like zeros and one, I'm sending it via the argument. So I'm just passing that. So these are all kernel code. So the kernel is basically taking care of these things internally. Now going back and seeing the IO. So we have one code here. So this is one of the, very complex code. So VL53L1, it's a name of a sensor, time of flight sensor. So this is used for measuring the distance of any device. So what happens, like, uh, it basically is having one photodiode, and which basically and one laser unit. So laser units basically injects the photons, and it's getting ejected by the sensor. I mean the whole sensor. So the sensor is consist of a photodiode and a laser unit. So the laser unit ejects the uh, your photons. Photons goes and hit some object, and then it comes back and received by the photodiode. And since it's a laser, which is light, so we know the speed of light. And when it went and hit the object, and when it came back, so we know how much time it has taken. So based on that, we calculate what's the distance of that object. So uh, internally, it's having a firmware. So firmware is taking care of all, because there we cannot run Linux. We need a core uh, C code, which is not even an RTOS, and which is based on a timer, because you are calculating because the speed of light is too much, very very high. So you have to calculate that very short duration of time, which can be done by the timer. So we are just measuring those time using the timer. But here we are basically requesting that firmware. So here the embedded software code is written, which is interacting with the other controller over the I2C. So if you see where it starts, so it starts from the probe. So the first entry point of this driver is this probe. This is the entry point of the driver. And our IO driver, basically, we hooked up with the I2C, the system bus now. So which system bus we are going to make use of it now is like I2C. And we have given our device a name as the name of the hardware. Okay, this table is, useless at the moment, because we are making use of the device tree. So we'll be seeing a device tree. This is a device tree. So what happens, the same code, I can make it to run on a number of hardwares. Only the thing is I have to change the device tree. So this device tree is meant only for Raspberry Pi 5. See the compatibility. If I have to, if I'll make this code to run on Pi 5, Pi 4 or Pi 3, it won't run, because I have to change this name. If I have to make this run on some different ST's board or some other vendor's board, then I have to change this compatibility and the address as well. Sorry, not this address. The GPIO's controller's name. Until or unless my device, the final device I2C address remains same, this will be okay. But this controller's name and this compatible strings we have to change, because we have to know that for which particular hardware we are making use of it. So that's a very easy one. It can be easily available in the datasheet. So next, coming back to the code again, the main thing you remember, you have to match this string with this C code. So these two must match, unless it won't get probed. So that device tree is getting loaded by your bootloader. In our case, in general case, it's like U-boot. In Pi's case, they have their own proprietary uh, bootloader. But how we configure that there, we basically tell there is a config file there. So we tell the config file that load this particular device tree. So we have to specify this name there. So this is also getting compiled, and it's getting available as a device tree blob. So during the bootloader loads this device tree blob, and when it loads the kernel, so we have to place this driver in a particular location. So when this string matches, the system loads this driver as well during the boot. If it's not happening, then we can do manual insertion as well. So first function is getting called is like probe. Is the first function probe, and what it do? So first we are configuring our I2C because I2C, okay, that's getting hooked up with the device, but we have to tell like with what kind of uh, value and what kind of registers, what's the width of the registers, because the final device is having I2C, it's I2C device, so it will be having its own register set and data set. So we have to tell that what's the width of that register set and the data set. Sometimes both of them are 16-bit, sometime both maybe 8-bit, sometimes it varies. Like in our case, the values are only 8-bit, but the registers, if all registers are 16-bit registers. So those are something which we are configuring. Then here, first time we are registering the device. So when we do this, everything will be taken care. So whatever we have discussed so far about the IIOs, like the buffer handling, the trigger handling, everything will be getting done here. So our memory is getting allocated and in few lines of the code. And then here, if you see, we are basically registering those I2C devices with the IO devices now. So here all the registration is getting happening is done. Then we are basically uh, configuring the triggers, like all the interrupts. So this interrupt handler, if you see, so that's the basically handler here. So at the moment, I'm not handling the data inside the interrupt. I'm just printing that interrupt because it's just for understanding that interrupt has been arrived or interrupt is working. Maybe something we can do in the future. So basically, this way we are registering the triggers. So it registered the buffer internally. So I'm not creating my own buffer. Everything is taken care internally. So that's it. I've just done all these setups and that's all. So next is these are basically the some configurations we have to do for the system to which is very much specific for the firmware requirements because there are something called timing budgets and measurement timings. So these are all in milliseconds. So we have to tell that after we started polling, how much time we have to wait until data has been received. And if the data is not received within this time, it will go for a timeout. So after this probe, when the data arrives, we will be getting that in a polling mode. So I just show you some commands here. Yeah. So basically, these are the commands. These are how the user space applications will be interacting using these commands to read the your device data. I mean, how much distance basically, uh, the target is on from the particular sensor. So we have some utilities. So you can basically wrap everything inside a script and run the script to understand that to basically test your IO driver. So I'll quickly go through the script. Wait, I'll just shoot directly on the target. So if you see here, my IO device, that is basically the device 0, as we see in our slides. So this is our device which got registered when the system boots up. And this is a Python script using which we are basically reading the sensor in every 1 second. So, okay, one more thing. One of the challenges which used to be there in the older IO driver was loading the configuration during the run. So that can overcome using this technique. So we can basically perform the open read write. These are all system calls. So using this open function, we can transfer the binary, the configuration to the target. So let's see. If you see the configuration cfg.bin, so that's the configuration. So without loading this configuration, the distance sensors won't work. The proximity sensor won't work. So basically, we have to load the basic configuration to it, which basically enables uh, the sensor, the photodiode, the laser, everything. So everything all we have wrapped inside this Python script. So let's run the Python script and see how it works. So we have just run the this script. So what's happening here? It's first loaded the configuration. So 91 bytes of this configuration, which we have in that binary file, has been written to the target. And now it start reading the sensor got activated, and it started reading the any object which is nearest to the sensor. So the sensor is kept over the table, and it's basically measuring the distance of the roof from it. So if I place some target on the top of this, so you'll see the distance will keep on varying. So now there are certain uh, targets kept over it. So it's showing 0 millimeter. So it's showing nothing on that. So when I remove the device, it is showing the actual uh, distance of the roof from the sensor, and it's all in the millimeter. So it's approximately 1.5 meter. Yeah. So uh, so this is just one demo. So far, any question from anything what we have discussed so far in the slide? Any questions? So I'll just show you a few things. So we were talking about the character drivers. So all the character driver appears here. So if you go and see that, because this device is registered as a character driver as well, so you'll be able to see that device here in the slash dev. That is IO colon device 0, this one. Plus this device appears in this bus. So here you're able to see two devices. Because I have two IO devices, I'm sorry, in this system. For another one, I have not enabled the character driver. That's a very simple plain driver for ADS 1115. And if you see that code is very simple. So here nowhere I have registered the character driver. So it is not appearing on /dev, but it is appearing on the sysbus. And this is basically an ADC. So you can read the channels. I mean, read any of these channels via this particular device path actually. Just show you one thing here. So we are not, suppose we are not sure that which devices we are using. So in that case, we can make use of. So this will tell you the device name. So these are two IO devices. So both are showing its name. So the device 0 is VL53L1X and the device 1 is ADS1115. Okay. Next. So, okay. Suppose I'm just going to read something for the voltage which is connected, voltage levels which is connected with the ADS1115. So I'll be using some commands like this. So only one input is connected, which is on the channel 3. So this is giving me some input. So since this device I mean, this particular channel is connected with 3.3 volt. So this is okay. Suppose I make this device to, I mean, this channel to connect with the ground. You will see a different number together. These are certain offsets which we have to fix via the calibrations. So all the test and measurement equipments are having some drift in their value reads. So we have to calibrate to basically get the actual reading. So these are under development at the moment. So it's not at all calibrated. So that's why you're seeing the difference, some drifts in the values. So I mean, I'm done with my demos. So far, any question from any of these things? Any I mean, any attributes? If you have any question from the attributes of IO or uh, anything from the IO subsystem or framework or something in general from the Linux. No questions? Sure. Okay. Then I'll stop here. That's all from my side today.
Yeah, it
Thanks,
was
everyone.
nice, Zafar. Yeah, thank you very much.
Thank you, Zafar.